Alright, so now we know about Boltzmann's entropy, we know the expression, we know that it's larger for states with a larger statistical weight, and not only that, but it's the only monotonically increasing function with the statistical weight that would still preserve the additivity property, So at least it has the basics that we would ask for an entropy function, but of course we still have to prove that there's more reasons to believe that indeed it is the true thermodynamic entropy, and to do that we need to somehow include in the formalism this notion of macrostates and be able to calculate explicitly the statistical weight of some macrostate and then see what happens with Boltzmann's entropy. So to do that, first of all we need to count microstates, and just remember, let me just change color as usual. Just remember that we are deciding to work, we're representing the microstates of a system in a high dimensional space, which is this gamma space, and any point in the gamma space is the full collection of coordinates and corresponding generalized momenta. So this is a continuous coordinate, okay? So it's not possible to count microstates because they form a continuum. So what we would need to do is to discretize phase space, okay? So we are going to break it down into little hypercubes, if you want, of certain volume. We're not going to elaborate yet on what that volume should be. It's just small volume, so that if you have a microstate which falls in one such hypercube of the phase space, you count it. If you have several microstates that fall into one such hypercube, you count them as only one, so you can distinguish them. And by this discretization, then you can count microstates. Otherwise, you wouldn't be able to. So just a notation thing, as in the lecture notes, I'm going to call the kind of, it's not really infinitesimal, but the small volume, which is finite, of this phase space cell. Let's just put the name here, phase space cell, and that is of course, well, the product of some increments in all the position or generalized coordinates from 1 to it would be what it would be fn, of course, and then from times delta p1 to pfn. Okay, so in total you have 2fn, which is what we had said before. Okay, fine. So if you have a gas, which is the system we're always thinking about, and this gas is non-interacting in any way. So on the one hand, for instance, molecules have to be really point-like particles without any volume. And because if they would have volume, then you would say that two molecules cannot come closer than a certain amount, which is twice the radius of this, if you like to picture them as balls or something, and that is an interaction potential. Okay, so you say they are point-like, so this kind of interaction for them being rigid is not happening, but also otherwise there's no other interaction potentials between the particles. If this is the case, you can say all the particles evolve independently from one another. They don't care that there are other molecules around because they don't even see them. So what you can do in that case, instead of using the full 2fn dimensional phase space, what you can do instead is to use a large collection of lower dimensional reference systems. Okay, so imagine that for each individual particle, you define the single particle phase space. I'm going to call it mu space. I'm going to label it. So this is the mu space of particle 1, and the number of axes here might be larger than 3, of course. So this would be what it would be? It would be 2f. Okay. Then you would have particle 2, another reference frame, identical, because all the particles are identical, but they are distinguishable, so I can label them. I can give them a name, particle 1, particle 2, and I can keep track of what particle 1 is doing independently of what particle 2 or 3 or n is doing. So I continue to do this thing. Let me just make them a little bit smaller here. So I make them smaller, I move this guy a little bit here, and I actually copy it because I'm going to draw the same thing, and I'm going to say that this is the last one. Okay, so this is n, and in between there are many of these spaces, and in each one of these spaces, well, the particle 1 will be here, and I can I can say the initial condition for particle 2 is there, and maybe the velocity is here, the velocity is doing that, this one, but the velocity may be doing this, and I can independently evolve particle 1 in time, and it will do some trajectory. Particle 2 will do, well, actually, really not that trajectory because the velocity is going the other way. But you see what I mean, okay? So the particles, well, they will evolve independently, not caring what the other particles do. If I then add up all of this information, I would have the same thing as the information I would get if I have the trajectory in the full gamma space. But this is only the case if the particles do not interact. So this is what, for instance, what happens in the ideal gas. So that's why everything I'm going to say now is thinking about the ideal gas. Okay. So fine. This is the single. Well, let's just write it because single particle phase space or mu space. Okay. So if we are going to work in the single particle space, again, we would like to discretize it. Okay, so each one of these spaces, we are going to discretize it and break it again into little hypercubes. Okay, and in this case, these hypercubes, let's say they have volume omega I, where I is 1 to n, and this is just the increment in the coordinates of generalized coordinates. So this is a vector, there's a bunch of them up to f, and the increment in the corresponding momenta that also go from 1 to f. Okay, so that's just notation, it's not really crucial. And okay, so now is when we can now is when we can introduce this notion of macrostates. Okay, so far we always look at microstates, we see how the system evolves in time, we say that to count microstates we need to discretize phase space, and any point falling inside of one of these cubes is going to be counted as a single instance of a microstate. We don't say anything about the volume of this thing, we just say it's small, but not how small it is, and in the end we're going to come back over the same point. And let me now do the following. So I will make the drawing so that you see what I'm saying. Imagine for a moment that you have a one-dimensional problem. Okay, so your molecules are one-dimensional for some reason, and this mu space is only going to be, well, some position, if you like, and some momentum, and nothing else, because there's no x, y, and z. There's only one coordinate and one corresponding conjugate momentum. This is the mu space of particle 1. And I'm going to make my grid that I told you, no? So instead of being hypercubes, in this case they are squares, because I'm in a two-dimensional space. And, I break my system, the relevant part of the phase space, into equal cubes, and I count them, and I see that there are m of such cubes, capital M. Okay, fine. Then, for particle 2, I know that it will be the same thing, because we have a single component system and all particles are the same. Okay, so all the mu spaces are the same. The only difference is that the label that I attach to them is different. Okay, so here I have mu2, here I have mu3, but they are the same in terms of the size, in terms that they have m cells, and in terms of the units of the axis and everything. Okay, so let me, I don't know, maybe make another one or another row of them. Let's make more to make my point clear. Yes, there you are. Okay, so now imagine that I'm going to allocate particles here. So there is a particle sitting in that cell, here there is another particle sitting there, here there is a particle sitting here, and here we have a particle there, and here we have one there, and here we have another one there. Okay, and many more, of course. And this would be, well, higher numbers, like n minus 2, n minus 2, n minus 1 in n. Okay, and here there are many more. So imagine now that I want to merge all of these things into one single space. So what I'm doing, if I do that, well, let's just do it and then I explain what is the consequence of this. So I'm just going to take and collapse all of these mu spaces into a single one. Okay, so let's just do that. I put this on top, and I put also this one on top, and I do the same with this one, and that one as well. Okay, so now I have lost some information because I have given up the label. So all of these dots are the same. Okay, so before I said that I have particles which are identical, but they were distinguishable. So I could attach a label to them and I could follow their individual trajectories. So this was what I was doing before. So now I'm saying I'm going to collapse all the mu spaces into one single mu space, which is here. And I'm just going to look at the occupation of the different phase space cells. So I say, for instance, the cell 1 has occupation. Let's just make a table here, cell, and here occupation. So it has occupation 1. In cell 2 there's nothing, in cell 3 there's nothing, but in cell 4 there's 1. And if you continue on in cell K, which is this one, there are 2 guys, and so on and so forth. Okay, so then you can keep track of how many particles are occupying a given cell in phase space, and what you're left with is an array of numbers. So what's the number of particles in cell 1, the number of particles in cell M, which is the last one. Okay, and this thing is less information than having the actual description, or you know which particle is doing what. Okay, so you know that particle 1 is in cell whatever in its own mu space. Now we don't know what particle 1 is doing. Okay, we just know the particles, the total number of particles that there are in each cell. And this thing is one kind of macro state. So we have lost information, and this would be for us in our calculations what we are going to treat as a macro state. Okay, so that's a macro state of my statistical system, and I need to calculate its Boltzmann entropy. So remember, the Boltzmann entropy is SB, which is proportional to the logarithm of the statistical weight. And the logarithm, just a remark here, this is natural logarithm. In the lecture notes I actually write this in LaTeX. Just when I write naturally, it just comes out like log. So, but it's always in base e. So there's no base decimal base logarithms ever in thermodynamics. So okay, so we need to calculate the statistical weight of the macro state we have at hand. And to do that, first we are going to do a pause and we are going to see a mathematical result. So this is Stirling's approximation, or Stirling's formula. Let's just write it down. Stirling's formula, which allows us to get rid of factorials. So imagine you have the logarithm, well, no, I was copying from the lecture notes, that you have the logarithm of that, okay? And you want to approximate this by something. So first of all, what is this, okay? So this is log of, well, let's just write it. This is log of n times n minus 1 times n minus 2 times whatever up to 1, okay? And the logarithm of the product is the sum of the logarithms, so what we have is log of n plus log of n minus 1, and all the way you go till 0, which is log of 1, okay? So if n is very large, okay, so then if n is very large, you could argue, okay, although, you know, we are just going to do it, and then in the end we are going to see that the result we get is actually correct when n is large. But when n is large, it seems reasonable to say, well, you can at least approximate this log of n. I know that it has contributions that are, you know, these logarithms of consecutive integers, but so it's a discrete thing. But I could make it continuous, and I could make the sum continuous, and I can turn the sum into an integral. Why not? So let's see if this works out, okay? So what I'm going to do is I'm going to integrate the logarithm of x dx, well, maybe, yeah, let's just write it like this. And I'm going to go from 1 to n, okay, which is what I have here. And if I do this integral, let me just check. You have to integrate by parts, and what you find is x, a logarithm of x minus 1, and you have to evaluate this between the limits of integration, which is 1 and n. And what you get out of here is x logarithm, it's n logarithm n minus 1, and then you have minus logarithm of 1. Yes, that's what you have, logarithm of 1 plus 1. Okay, so this is 0, and here, because n is very large, as I was saying, you have a term here which is of order n, a term which is n times logarithm of n, and just an irrelevant constant which you just throw away. And then you can say, in the end, that the logarithm of a large number might be well approximated by n times the logarithm of the number minus 1. Okay, so let's just try that out, and if you take a large number, do the logarithm, and you see that this approximation is really, really good. Okay, so that's what we are going to use to get rid of the factorials that are going to appear inside logarithms, because this statistical weight that we are going to now calculate for our macro state is going to contain factorials. Okay, so how we calculate that? Well, let's see. First, let's write again or let's just maybe put a title here: statistical weight of a macro state. Okay, so the specific macro state we have in mind to be able to calculate things and arrive to conclusions is something like that. Okay, so there are certain finite volume cells in a single particle phase space that we collapse on top of each other, and we lose some information. And remember, again, very important, not so important now for this lecture, but you will see in the next synchronous lecture when we deal with indistinguishable identical particles, with quantum statistics, then you will see that it matters whether your identical particles are distinguishable or are not distinguishable, whether it makes sense at all to say I give a name or I label a particle and then I can track down its individual trajectory. If you cannot do that, which happens with identical indistinguishable particles, then the way you calculate statistical weights of a macro state is different. Okay, so let's just think that this is what we have to do. That's our prescription. We have a bunch of boxes, m boxes, and we have a total of n particles. They are identical, but I can distinguish them. Okay, so how many ways are there for me to take n 1 particles out of the box full with, big N particles? Okay, so I have a large number of particles here, yes, and I have to fill in my array with, if you like this, I have m little boxes like that. Okay, so I have to make sure that in box 1 there is n1, exactly n1 particles, and in box 2 there is n2, and in the last one there is nm. So how many ways are there to do that? So how many ways are there to pick n1 things from the box with a total of n particles? Well, I can extract the first particle, and for the first particle I have n choices. Okay, I'm going to call this thing that I'm going to calculate, I'm going to call it omega, so number of microstates, or number of microstates when it comes to filling the first box. So the number of arrangements to fill the first box. Then I will calculate the number of ways to fill the second box, and I will calculate in the end the number of ways to fill the last box, and the total statistical weight of my arrangement of my macro state, which is n1 to nm, is going to just be the product of all of these things. Okay, so j from 1 to n to m, to m of these things. Okay, so let's see what is the first one. For the first particle that I extract from my box of n particles, I could choose any one of the available n particles. Okay, but the second particle I only have a choice between n minus 1, because I already removed one. And the third particle, it would be out of n minus 2 possible choices, and so on and so forth. And this ends when you run out of, when you already took n1 to fill the first box. Okay, so the last particle you get out, you have n minus n1 minus 1 possible choices. Okay, and there you stop. And because okay, this is the way you pick particles, but it doesn't matter how do you order these particles inside the box, because it's the box. You just throw them in the box. You don't put them in any particular order. It doesn't matter which is the order in which you pick these particles, as long as you pick those particles. So what happens here is that all permutations of these n1 particles that you picked, you should divide by all of these permutations, because all of these permutations are equivalent. Okay. So once again, you have to pick them one by one, and this is up here is the different choices that you have. For the first one you have n choices, for the second one you have n minus 1 choices. So a particular string of particles that you took out of the big box and you put in here has, it can be chosen in this many different numbers of ways, but I don't care which order I pick the particles, as long as in the end they all end up being in the same box. So that's why I divide by all possible permutations of n1 particles. Now what happens for the second one? Well, for the second one, how many choices I have? To begin with, I have n minus n1 choices, okay, because this is the number of particles that are left. For the second particle is n minus n1 plus 1. And there you go until you arrive to n minus n1 plus n2 minus 1. That would be the last one. Okay, and once again, because you're picking this n2, you're throwing them in the same box, you have to divide by all the possible permutations of these identical particles, which is n2. Okay, because you do not care in which order you picked those particular particles, because you are going to anyway throw them in the same box. Okay, and you keep doing that till you are done, and you can see what emerges here. Okay, so you can see what pattern is emerging. When you multiply all of them, let me just remove this so you know that this is just, I will put it closer like that. This thing is going to be the product of the first product until the last. And if you take the first, you look at the numerator, you have n times n minus 1, n minus 2, n minus n plus 1. And here is n minus n1, n minus n1 plus 1. So you see that you are completing the factorial. So when you add all of them up, so you multiply all of them, the numerator gets every single factor in the factorial of n prime. Okay? And in the denominator, what you have? Well, for the first one you have n1, for the second one you have n2, and there you go until you arrive to nm. Okay, so this thing here is the statistical weight of the macro state n1 to nm, if the particles you're talking about are identical but distinguishable. Okay, these are how many possible different choices can you make out of a total of big N particles to distribute them in these boxes according to these occupations. Exactly N1 in the first box, exactly N2 in the second box, and exactly Nm in the last box. Okay, so this is the combinatoric number that we care about. Okay, so of course I assume many of you will have seen combinatorics before, and maybe this is familiar, but I'm just trying to explain it step by step, so that without assuming you know the combinatorial numbers or you remember them, because what happens to me personally is that I always forget. So fine, now we know what's the statistical weight of this macro state that we built when we forgot about the labels of each particle. This is what we chose to forget in order to take a microstate and turn it into a macro state. Okay, merging single particle cells, so we lose track of which particle is which. Okay, so fine. Now let's calculate the Boltzmann entropy of this thing. Let me just have this. Fine. So what we have to do is to take the logarithm, but you remember Boltzmann entropy is just proportional. Okay, so let's just think of Boltzmann divided by the Boltzmann constant, and this is just the logarithm of the statistical weight. Okay, now statistical weight, we have said in this particular case, is n factorial divided by n1 factorial up to nm factorial. Okay, what you have here is, well, logarithm of n factorial minus logarithm, well, minus the sum, if you want, from 1 to m of the logarithm of ni factorial. But we saw Stirling formula, okay? So what happens with these logarithms of large numbers? Well, this n is a large number, so I can for sure do n, so this is approximately equal to n logarithm of n minus 1. And here comes the big assumption, okay? Before, when I partitioned the single particle phase space into boxes, I said that the boxes were small, but I didn't say how small. Certainly not infinitesimal. They have a finite hypervolume. Now I'm telling you that they are large enough, okay, they're small, but large enough to contain a large number of particles. So I'm going to assume that the occupations here, the occupations I have are 1, 0, or 2. But, I'm going to assume that these cells are actually large enough so that if I have a very large number of particles, in the end, in every single box, there will be a sufficiently large number of particles so that I can use Stirling's formula to approximate the logarithm of the corresponding occupation factorial. Okay? Now, this is a problematic assumption because in reality, we will see it in the end. Okay? In reality, this is not going to be true. Okay? However, we can do a fix in the theory, and we can still be sure and certain that all the formulas and results that we are going to obtain, which all rely on Stirling's formula, Stirling's approximation, are still correct anyway. Okay, in the end we are going to see that, okay, this assumption is not really correct, but we are lucky and somehow in the end everything works out nicely. But so far, the assumption is that this ni is large enough, and this is what Boltzmann himself assumed, okay, but it was not correct. So we go from 1 to m, and this is approximately equal to, let me make some space here, there we go, and this is ni minus, logarithm of ni minus 1, okay? And here you can simplify things a little bit, because you see what you have is n log n, then you have minus n, and here you have minus, let's write it separately, the sum of ni log ni, and you also have minus, so it's plus, the sum from I to m of ni, okay? But you know that the total number of particles, if you sum all the occupations of all the cells, you get n, so this thing is n, and this minus n goes with the plus n, and what you get in the end is that Boltzmann entropy of that particular macrostate divided by the Boltzmann constant is n logarithm of n minus the sum from 1 to m of ni logarithm of ni. Great, so that's it. This is the statistical entropy of an arbitrary macrostate, in the single particle phase space, when the only thing we have is the occupations of phase space cells. Importantly, I'm going to remark this, which I said in the previous part of the lecture, that this macrostate does not need to be a macrostate of equilibrium. I didn't say that the system is in equilibrium. I just said, I took the state of the system, I merged all the single particle phase spaces, but I never said that this configuration corresponds to a gas in equilibrium. It's a gas that may be out of equilibrium, and nonetheless, this statistical object, statistical entropy, can be calculated for such a macrostate. Okay, so what we are going to do next is imposing that this entropy is maximized, okay, assuming that this is the true entropy, and therefore it will be maximized if I ensure that my system, my gas, is adiabatically insulated, then I will obtain what are the equilibrium occupations. So which would be the occupations of the individual cells of phase space if I impose that the statistical entropy has to be maximized. And then we will see the consequences of that.